And then you guess the solution, you plug in, etc., right? It's a little bit harder guess. What function when I take two derivatives and then I add a constant times the first derivative and then I will have a constant times the function equals 0, right? That's a little harder to guess, right? But you use a little intuition and you can get that the solution is similar to last time. We just put an exponentially decaying part in it. A e to the minus b over 2m times sine or cosine, doesn't matter, omega t plus phi. Right, that's the damped oscillator. Just like that. Okay? Let's see. Now there's some interesting things about this damped oscillator. You can say it looks just like the other one, except now the amplitude is decaying. Right? So we could say, one way to analyze it is say the amplitude decays. So you could think of it as the amplitude as a function of time. Right? Basically this part. Oh, there's a t missing. There you go. The amplitude as a function of time is sort of like you could say, how do I want to say it? It's like a naught, the original amplitude, e to the minus b over 2m t. So we'll do some exponential functions in a minute, but if you can probably visualize what that looks like. You start at a naught and it comes down. Just like what's been happening here. Our amplitude was out here. What happened, right? Now it's all the way down to there. There's our amplitude. We lost that much. It's not moving in a liquid, but still, it's a resistive force slowing it down. One other little thing happens when you go plugging things into here is that the omega is slightly different. Okay? So that's why with no damping, I like to call it omega naught. This is the natural frequency where it wants to go. But if you have damping, your omega comes down a little bit. It's the square root, in this case, of k over m minus b over 2m squared. Like that. Comes down slightly. So the units work out. Do we need to be able to find x on our own? If yes, what are some strategies? No. Yeah. You're not going to have to guess x. You're not going to have to guess a solution to something like this. This is just for enrichment. Okay. That's like differential equations, and we've now done the only two that you can guess. So there's none left. But I just wanted you to see that's how the same process happens every time. You apply Newton's laws, you get an equation, you come up with a solution, you plug it in, and then you get the full solution. So we've got this amplitude now. This is free, and this is decays, just like you're seeing. The frequency is reduced, but it's very small. Like if you look at typical numbers, it comes down by like 1%. So you can't really tell the difference usually. If the damping is really big, then it might not oscillate. So there's whole ranges of interesting behavior here we're skipping over. We're just talking about the typical sort of lightly damped system. But mathematically, this comes from plugging this into here, basically, and solving for omega. Okay? And now if we wanted to plot it, it would look like, let's see this. All right, so, well, I did a sine, so I've got to start here. But it's got some big amplitude, and the amplitude just goes down like that. All right? That's not a good drawing, but that's horrible, actually. But that's sort of roughly what it would look like, except it usually have a lot more cycles than that. So this is x versus t, the position versus time. And you can kind of draw this dotted line like this. It represents the decaying amplitude. Represents this thing, minus e to the b over 2m t. Right? So just visually, that's what it looks like. I keep setting my phone down. Yeah. Okay. Okay. Yeah. Okay. So we'll stop now. We'll do a sample problem of that in a minute. Yeah.